Hello everyone, I am Ravindranath from Department of EC. I am here to present small analysis on automatic street sweeping robot. What is automatic street sweeping robot? It is a mechatronic system designed for autonomous street cleaning. What are the key integration done in this project? Mechanical sweeping mechanism, motor driven propulsion system, proximity based obstacle avoidance, closed loop PID feedback control. What was the challenge faced in ASSR? Main challenge faced is maintaining desired voltage when disturbances like dust, load and sudden obstacle appear. A PID control ensures zero steady state error and acceptable transient response. This presentation covers system identification and component description, mathematical modulation, control system block diagram, disturbance effect analysis and Matlab implementation. System description and components. Majorly it has four systems: sensors, PID controller, motor drive, plant and obstacle module. We have different types of sensors used in the project, and PID most preferably STM32 is used. Motor drive we use pulse width modulation hex bridge power amplifier which translate power digital signal to motor voltage or current. It acts as actuator amplifier in the control loop. Plant and obstacle module. It has two DC motors plus differential drive mechanism, and also when object is detected it reverses the wheels. Mathematical modulation. Transfer function of different systems. Given here are the parameters used and their corresponding transfer function for each of the systems, and this is closed loop transfer function of overall system. Block diagram. Reference input is given to summer where it arises an error, and error signal is given as input to PID controller where output control signal is obtained, which act as input to motor drive amplifier where we get drive signal for the plant system to run. And in this plant system you will have two disturbances majorly, we will discuss in next slides, and feedback loop is connected through sensors where error is reduced using this feedback network. So we have two obstacle, one at dust load and object detection at the other end. Disturbance 1, it lies between motor drive and plant. It makes the bin fill which increases motor load torque. How can we reduce this effect? When integral accumulates 0, it drives steady state error to 0. Without integral gain, permanent velocity offset result. Disturbance 2, we have obstacle reduction. Entry point will be reference input at summing junction. The cause of this disturbance is IR or ultrasonic triggers. How can we reduce this? Is to make derivative gain predicts damping ratio such we can avoid overshoot error. And we have other two minor disturbances like surface evenness and even battery voltage plug, which affects the accuracy of the system. And here are the Matlab Simulink implementation, and here are the steps: giving opening Simulink, giving reference input and making summing junction, providing values to PID control, giving transfer function to motor drive and disturbance system. And here is the block diagram that is being implemented on Matlab. It is the code used in the Matlab, and each section will explain about its transfer function, open and closed loop, step response and information metrics and stability of the system. And this is the output obtained after simulation. At 0 second it starts and get a maximum of 1 meter per second with 5% overshoot, and gets settled at 0.6. At 3 seconds there is a slight brief dip where integral action makes the signal restored at 0.8 meter per seconds. At t6 seconds the obstacle gets stopped, which means the velocity becomes 0 and derivative damps oscillation cleanly. And here is the result and the stability analysis. Overall we have got very good result when compared to expected. We got very good output here. So for rise time expected was 0.8 but we observed at 0.3. Settling time was 2.5 as expected but we got 0.6 as observed. Then overshoot is less than 10 which is impressive. And SSC is 0, margin drain is greater than 6 dB and recovery after DOP is also less than 1.5. Then proportional gain. It is used to correct the speed. Higher proportional gain, faster response but may cause overshoot. Integral gain. It eliminates steady state error from the dust load. It is very essential for disturbance rejection. Derivative gain. It predicts error trend. It damps oscillation during sudden obstacle stop. In conclusion, the achievements we achieved through this presentation is we have completed closed loop PID architecture with all the Laplace domain for every subsystems. We have seen their block diagram. We have confirmed how those integral and derivative gain has helped us to make the system stable, and Matlab specification. And here are the future work which can be done. Adaptive PID tuning for varying dust load, GPS based autonomous path planning, steady state multi-variable controller, real-time STM32 embedded implementation, LiDAR based lab for indoor mapping. Thank you.